drastic change in topics from the last presentation. The next project was provided by Commonwealth Engineering. I would like to acknowledge Brent Hazenor and David Hines from Commonwealth. They spent a lot of time with students. They hosted them at their office for progress reports, and they even arranged a field trip of City of Newburgh wastewater infrastructure. So they really did an excellent job as a liaison, mutual liaison. So it's my pleasure to introduce Jacob Cox on the far left, Shane Williams, and Ben Vasquez.
Thank you, Dr. Hill. So, as he said, my name is Benjamin Vasquez. These are my partners, Shane Williams and Jacob Cox. And we are here to present our trunk sewer and pump station design in Newburgh, Indiana. So, Commonwealth provided us with this project, and they tasked us to complete certain objectives listed behind me. Our first objective was to eliminate 3 existing lift stations to provide service to current Newburgh subdivisions. We will then design a gravity sewer system which will serve existing land and projected land development. This gravity sewer system will flow into a lift station we will then design. This lift station will pump through a force main we designed that will ultimately end up in Newburgh's master lift station. Now that our objectives have been defined, I'm going to pass it on over to Shane, and he will explain how we started our design.
Thank you, Ben. This is the base map that we had for the projected land development. It basically involves this square right here. You can see the ditch line essentially cutting the land in half. The total area here was around 835 acres. The red dots represent the existing lift stations that will be removed. On the far left is the Kenosha lift station. In the middle there is the Willow Pond lift station, and to the northeast is the Houston lift station. These are just kind of what the structures look like. So in the top right here, this is your housing. This is where your electrical components would be along with monitors so the workers can come and check things. The bottom right here is kind of what we're designing. This is the concrete structure. Within that, the gravity sewer would then have flows coming in. 2 submersible pumps would be in that, pumping out the sanitary sewage via force main. On the far left is the Willow Pond lift station, so this existing lift station here. Like I said, these will all be removed and redirected to our trunk sewer. This is the projected land development by 2021 according to the Town of Newburgh Comprehensive Plan. All the yellow represents residential land development. As you can see on the far east here, there's also a school potentially going to be built by 2021. So when flows were calculated, this all had to be accounted for. So when this development would occur, it wouldn't all happen at once. So we broke it down into 5 different areas, A, B, C, D, and E. This is another layer we created. So within those areas, we would have undeveloped area and developed area that's already there. Blue represents developed, pink represents undeveloped, and of course we have the school layer here. There's different zones that we had in these areas. So we had like D1A, D2A that just represents developed zone 1 in area A. This would be an important zone right here for us. This is where we calculated our density factor to calculate the amount of houses that I will explain here. So what we did was in GIS, we calculated the total area for that zone, which was 16 acres. We then calculated, or we counted houses in that area, which was 40 houses. We then came up with 2.5 houses per acre. This is how we would get the total number of houses for all of the undeveloped area. We then took it to the Indiana Administrative Code, where it said for single-family residential homes, the average daily flow would be 310 gallons per day. The peaking factor for this would then be 4, so we would just take the average times 4. We also found the minimum daily flow, which would just be 20% of the peak daily flow. So this is kind of a breakdown of how we calculated flows. We had total area, houses, average, peak, and minimum. These are all the different zones up here for developed and undeveloped. And then we had grand totals for area, houses, and so forth. So for this area alone, the peak flow would be 335 gallons per minute. This is just a breakdown of each area. So this chart here represents Q Peak and Q Design. Q Peak only represents the developed land, so the houses that are already there. Q Design would be what we designed from, so the developed and undeveloped land. This chart here excludes Area E because it would have its own separate pipe eventually into the lift station. It wasn't involved in the sizing of the pipe for the trunk sewer. So the total there would be 3.4 cubic feet per second, excluding E. Now when we include E, we needed to do this so we could size the lift station along with pumps and so forth. So when we included that, it came up to 3.9 cubic feet per second, which is around 1,700 gallons per minute. These next few slides I'm going to go through fairly quickly. They're just elevation profiles. It's kind of a preliminary step for our route selection. As you can see, we stayed on the west side of the ditch line. We had to be at least 10 feet away from it. What we're looking for here is just sudden drops in elevation or rises that would prevent us from laying the pipe at minimal slope or increasing velocity in the pipe. We stayed on the west side all the way up until Willow Pond Road. Once we crossed Willow Pond Road, we switched it over to the east side. I'll explain why in a minute. This is a separate segment here coming from the Willow Pond lift station, so just looking for sudden changes, but we're going to be at least 6 to 7 feet underneath the ground anyway. So the reason we switched to the east side was the location of the lift station would be right here, so we just didn't want to cross the ditch. We wanted to cross the ditch as few times as possible. Once we kind of did that as a preliminary step, we went out and actually took a field survey. What we were looking for here was just different elevations or any other objects that we would need. We used GPS units, so the Trimble R8 and R10 rover. The Trimble data logger here was how we actually took points. This is a picture of our complete units that we used. So the first thing we had to do was set a control point. So when we were out taking all these other points, this point here would be here for reference to get our X, Y, and Z coordinates. Every 100 feet, we would take a cross-section of the ditch. These are the shots that were involved in the cross-section. On the far left is a grade shot, so about 10 feet off the ditch line. In the middle, we have a bottom bank and flow line shot, so the bottom of the ditch, and when we could reach out, we would take a flow line shot. On the right here is a top bank shot, which is just the top of the ditch. Between each cross-section, we would take 1 or 2 points as well, just for elevation changes. This is our complete survey data back on our base map. There's quite a bit of data here. I think it was around 1,600 points. We did both sides of the ditch just to have a thorough survey. So once we had exact elevations, we could then start sizing the pipes, which Ben will elaborate on.
Thank you, Shane. So as Shane explained earlier, we have our Q Peak for currently developed land and our Q Design for projected land development. And now that we have done a survey, a complete elevation profile has been developed. So our first step, we assumed full flow in our pipes and we used Manning's equation. In Manning's equation, we used the flow rate calculated earlier, along with minimum slope requirements provided by the 2008 Town of Newburgh design standards. These were plugged in to solve for the diameter. Pipe sizes were then rounded up to eliminate the amount of times we had to switch pipe sizes. This would also help us save on cost. And then velocity checks were calculated in order to make sure we met the cleansing factor of 2 feet per second. And this was because partial area flow conditions were in our pipes throughout our system. So as you can see here, these red dots are load points in our areas explained by Shane earlier. Flow rates were applied at these load points, which gave us a size of 12 inches from 1 to 2, from 2 to 3, 15-inch pipe, 3 to 5, an 18-inch pipe, from 4 to 5, a 10-inch pipe. This is because area E has its own separate flow. And then from 5 to the lift station, an 18-inch pipe. Here's the layout of our final gravity sewer. As you can see here, the total length will be around 7,936 feet. Also, I want to note that when crossing a road here, we have to bore underneath the ground perpendicular. So every sanitary sewer requires searchable manholes. These are represented by blue dots. Indiana Administrative Code provided us certain requirements we had to meet, which is a manhole cannot be placed, and has to be placed at can only be placed at a maximum of 400 feet. Also, we have to place it at every direction change, pipe size change, and every significant change in slope, and before and after you cross the road. We came to a total of 30 manholes. So here's an example profile of our pipe depth. As you can see here, the crowns of each pipe are aligned. A manhole is located at a change in slope, and then our invert elevation follows the minimum slope requirement all the way until we get to our pump station. Our final invert elevation into our wet well will be 16.5 feet. So now that this elevation is known, our pump station and our force main can be designed. I'm going to let Jacob go into more detail on
Thank you, Ben. As you can see, the force main route starts where the lift station will be designed. Where the lift station will be placed here and heads north along this road up to the master lift station where the sewage of Newburgh goes. As you can see along the route, there are two rather large hills along the route. This makes selecting a pump for this project very difficult due to the large amount of elevation that we'll have to pump through. The total length of this force main is about 14,000 feet. It's about 2.8 miles long. And due to requirements by general standards where sewage has to flow 2 feet per second through the pipe in order to keep the pipe clean, a diameter of 12 inches was necessary so that the fluid through the pipe would flow at about 5 feet per second, so not too fast and not too slow. A total of about 35 manholes are along this route due to the requirements that a manhole be placed every 400 feet. And air release valves were also placed along the route at every high point or every 2,500 feet. This is just a drawing we made in AutoCAD that shows the large difference between the water level in the lift station and the highest point in the pipe. This is just some basic information about the wet well. The biggest points here are that the diameter of the well is 12 feet and that the capacity within the wet well is about 9,300 gallons. This is a cross-section of that wet well that we drew in AutoCAD. As you can see, the pump down here pumps the fluid into a pipe that's about 8 inches in diameter and goes into this valve vault, which will be discussed here in a minute, and expands from 8 feet into a 1 foot pipe, or 8 inches into a 1 foot pipe. This is a schematic of the valve vault that we drew. As you can see, the fluid flows in and then goes through these check and plug valves that will be on each pipe until they merge into a single pipe. This picture on the right is a picture of the valve vault at the Houston lift station that's currently in place. In order to select a pump for this project, we had to develop a system head curve. And to do this, we had to utilize the pump head equation, which is made of two major components. The static lift, which is the elevation between the water level and the highest point in the system, and the energy losses within the system. Pump selection is based on a few factors, mainly the flow capacity of the pump, the head that the pump can provide, and the efficiency of that pump. Due to these factors, we decided to go with the Flight C3300 due to its higher efficiency. These next 3 slides are just a few examples of pump curves from the manufacturer with our system head curve drawn on. As you can see, this pump from Cornell has a total flow capacity for this project of about 2,080 gallons per minute, with an efficiency of 60%. This other pump from Cornell has about the same flow capacity, but a much higher efficiency of 76%. And this is the pump that we decided to go with. It provides just about the same amount of flow with just a little bit more efficiency, which is why we chose this pump. And now I'll give it off to Ben to talk about the cost analysis.
Thank you, Jacob. So as you can see here, with our final design completed, our main expenses are our new lift station, which include the pumps, and our force main routing all the way up to the master lift station. I also want to note that in this manhole subcategory, it includes the manholes from our force main and the manholes from our gravity trunk sewer, which brings our grand total to around $2.8 million. Also, a 10% contingency was applied to account for any unaccounted for costs and anything that may happen during construction that would cause extra cost. And also, we kind of kept track of our hours, paid each other $10 an hour, came up to $2,500. So we'd like to give acknowledgments to Brenton and David Hines from Commonwealth Engineering. As Dr. Hill said, they helped us a lot throughout the semester, provided us with lots of guidance. We'd also like to thank Shane's brother, Shelby Williams, for staying with us 10 hours on a Sunday to complete our survey. Leroy, I don't see him in the audience, but he was able to give us a tour of all our lift stations and the master lift station. Dr. Jason Hill, for meeting with us multiple times a week, keeping us on task, making sure we completed the project correctly. And of course, USI faculty for providing us with this great education. And Donna, the engine that runs this engineering program, kept us on task all semester. Here's our references. Now we'd like to open the floor to any questions.
All right, questions?
Good job, guys. You showed a picture with a large hill you had to overcome. Does it ever make sense to bore through the hill and try to keep the pipe more level rather than going up to that high elevation?
It can make sense so long as the cost of digging a hole that deep would outweigh the cost of a new pump that could supply that type of head.
Thank you.
Was there any significant difference in the different pumps with the different efficiencies, difference in costs?
I tried many times to get in contact with these pump companies to get a price. For whatever reason, they don't list anything on their website. So anytime I called them, they were either out of the office or busy with another client. So I never got any actual cost from them.
When you go to page 20, or slide 20, the force main follows roads. But it looks like with the yellow in the new subdivision, it doesn't look like it's going to follow the way a subdivision would be laid out. So how do you handle manholes coming in at angles with what might be perpendicular and horizontal roads?
Within the force main?
Well, no, the force main following roads, it appears, but the yellow is coming in at an angle. So how do you handle following roads, future roads? We don't know what they are yet. How do you handle that?
These were just. We didn't anticipate any roads to start off with. We just, due to our survey, just gave us elevation profiles. So like those 30 manholes were either located 400 feet apart, or whenever our slope was a drastic change, whenever our pipe changed size, or whenever. You can't see it here because it's such a far shot. Those pipes aren't necessarily all straight because of the way that ditch line curves. So there's multiple changes in direction. When the development happens, I'm sure they might be able to adjust that, tie into those manholes as best they can.
The idea was just to follow the ditch line from the start, so we didn't really anticipate roads being developed or anything like that.
I can speak here. What? There you go. Aw. You know. With the new updates in terms of CSO overflow or water, rainwater overflow, was that taken into account for these pipes since they're trying to put it all in the sewer system now?
The system here is actually not a combined sewer, so it's separate sanitary sewage, and your rainwater is going to be separate from a sanitary sewer.
Thank you.
All right, any other questions? Let's give them a hand.